David, it's a great pleasure to meet you and to have this opportunity to pick your brains. My questions are on a high level, but somewhat sort of practical level. And perhaps to start, just mention, from my perspective, there's been some spectacular advances recently in artificial intelligence. And I think first I noticed it in speech recognition and then in vision processing, and probably most recently in text processing, where some truly amazing stuff has been happening. But my perception is that these things have come from extremely well-funded organizations with enormous data centers, with power stations used to power them. I think I heard somewhere that GPT-3 needed millions of pounds of just compute resource to do things. So I'm wondering, to what extent is AI becoming a game for large corporates? And is there any room for smaller companies or perhaps even individuals to get involved and to advance the field?
That is a really good question. It's an unqualified yes. So there absolutely is. Of course, as you pointed out, there are models which are true leviathans, which you need a massive data resource, computing resource to be able to construct, let alone to experiment with. But there's plenty of branches of machine learning which rely on so-called small data, where doing more with less is the name of the game. And modern machine learning has got really good at doing that. So there's a huge amount of, we've talked about the use of uncertainty in engineering and the use of using uncertainty in machine learning systems, so that when they produce a prediction or give you a classification or whatever it might be, there's some notion of handling uncertainty in a principled manner. It's much, much easier to do probabilistic systems which are not at the GPT-3 scale. So you will notice that a lot of the true leviathans of the models, they tend not to take this uncertainty aware principle, because it's already a massive job to be able to handle that huge amount of the huge architectures of the models and the data themselves. So absolutely, whether it's one person with a single GPU in a single desktop system, there's a huge amount of work to be done on principled machine learning across the spectrum. So this is why modern machine learning, when I was growing up, machine learning used to just be in engineering departments in the UK and in globally in computer science departments. And now it's spread as a result pretty much of what you said. So maths departments, statistics departments, computer science departments in the UK, as well as engineering departments. Now there's machine learning people across the board, because there's contributions that everybody can make, no matter how big or small their systems are. The big complex model has got its place. I've got one lab with a walk-in computer, literally. It howls like a jet engine, and you can go and get your hair dried in it. It's by walking into it. But there's a lot also that you can do that's important, as I was saying, on smaller scale reliability engineering. So for example, AI in your phone, it's not going to be running these mega heavyweight models. It's going to be running something much more parsimonious, much more designed for the constraints of the phone in your hand. And those are the kind of projects that literally anyone can get involved in.
Do you have any sort of favourite examples of those? Or?
Well, in my field, in healthcare, there's a huge amount of really exciting stuff in enabling access to healthcare. So in places like low and middle income countries, where not everybody is highly trained cardiologists, let's say, or you don't have access to really very well trained clinicians the way one might hope and expect in OECD countries. But there are healthcare workers. I do projects myself in rural China and in Vietnam, both classified as low and middle income settings. And you can put a phone into the hands of a healthcare worker, and the phone does some of the of the monitoring, some of the interpretation of the data, and presents those results to the trained healthcare worker, you can really improve a lot of people's lives by doing things like that. And those are not mega models running in a multinational data center. They're little things running on someone's phone, talking to local sensors.
Is that in the sense of seeking to apply some of the techniques that come from the big corporations to sort of put them into more modest computational contexts? Or is there sort of different technology involved in that?
It's probably the latter. So if you try and translate GPT-3 into a really small system, it's going to fail. So the constraints of everyday life, where you don't have a mega data center on hand, in some branches of engineering, this is called like the edge, where the edge refers to right next to the point of use. So whether it be the person's phone or whatever it might be, or body-worn sensors or some sort of watch, if it's a setting like that, they've got constraints, hardware constraints on the complexity of models they can run. There's all sorts of communications constraints to the cloud, whether it be because you don't want to destroy your data allowance this month on your mobile phone provider network, or whether it's because the network doesn't exist, maybe in a remote setting, or Wi-Fi is not available. Maybe it's a low and middle income setting where communications are less reliable. So all of those constraints mean that there's different kinds of engineering that you do. And you can take ideas from large models, but by no means is that the start and end point. It's really a whole branch on its own, I would say.
Just following up on the large model issue, I have a little bit of a niggling worry about this, because if you were teaching a computer to learn using current techniques, you would bombard it with gigantic amounts of data. And yet, when a baby learns to talk, it isn't presented with the entire content of Wikipedia before it utters its first word. And I think there are many examples in human learning where, I think the baby example, I forget where I read it, but it's an astonishingly small number of words that a baby is exposed to in the first 1 or 2 years of its life before it starts talking and actually then conversing quite fluently. So are we missing a trick here? Is there something going on here, or is it just that evolution has done all of the large scale?
Very good point. Well, let me answer that, but I probably wouldn't want to step out of, I'd be speculating. I'm not a developmental scientist. I'd be speculating were I to say, how a human learns. But I do know how machines learn, and there's a lot that one can do. It is not necessarily the case that one needs, as we were saying, one needs vast quantities of data to construct a model. And in some cases, that's not the right thing to be doing anyway. So in my field, in healthcare engineering, it may be that there's a rare disease you care about. You don't have the luxury of vast quantities of examples of this particular rare disease. And also, human variation is such that you probably haven't covered all of the complexities that could exist within this rare condition anyway. So the notion that you must completely exhaustively supply to this machine during the training process all the possible things that it could ever hope to come into contact with, and some meaningful extrapolations or interpolations and augmentations of the data set thereof, I don't necessarily think that's true for many real world applications. So as I say, in the rare disease modeling case, it comes down to, can you perform meaningful predictions and meaningful inference using limited data? So we've talked about limited constraints on hardware and how that changes the technologies that you can apply. If you've got very limited data, also then there are different technologies that one needs to think about. Are you retraining and tweaking bigger models that are analogously trained on something else? So I've seen one really cool paper that was trained on Google Street Maps, and then it was being used on the arteries in the brain because they looked a little bit like street maps, and performance was boosted rather than just looking at medical images, because there's a lot of Google Street Maps available, and so on. So that's just an example of the fact that there's either opportunities to port in bigger complex things that you've constructed previously, or to really construct small data models that handle the limited knowledge that you've got in a reasonable way. And I say reasonable in a manner that means that you're taking into account all the uncertainty, both in the model itself. We recognize that the model's not going to be perfect, and also in the data. We recognize that the data are probably artifactual and noisy as well. And I really think that's where, I'm an engineer, I would say this, but I really think that's where engineers come in, because we really like dirty, noisy, artifactual data. It's a real world game. If all the data was super clean and well curated, then machine learning would be far, far easier than it is, and it would be a pretty trivial exercise. In most real world applications, the data are gritty and the problem is not obvious, and even the model that you use may not be obvious.
Speaking of data, dirty data in a different sense, as recently as 2007, 2008, Barack Obama was running a campaign, and he was quite proud, and he received quite a number of plaudits for the modern digital campaign, his use of data, his use of targeting. And I think if a politician were to boast about this now, they would get a somewhat different response. And that's changed in quite a short amount of time. Data is now sort of almost becoming the new radioactivity, in the sense of the stuff that you need to be careful with, you need to worry about, and certainly in the realm of politics. And I wonder whether any of that has spilled over into your work, and whether the things that the type of data that you could use and what you could do with it in an academic context is now very much more constrained from that sort of societal point of view.
Bear in mind that I work in healthcare, right? So we've had some fairly high profile, and rightly so, bits in the popular press about healthcare data and so on. I think that really just reflects society's understanding that data, particularly about one's physical condition, about one's health, one's mental health, they need to be treated with respect, and that's why medical ethics exists. So in my world, you don't use patient data unless the patient has consented, or you've got reasonable approvals from central government and NHS ethics, etc. So in my world, it's very well regulated, and for a good reason. It makes research hard, so all that regulation does mean that you can do less, but I think probably it's a net gain. Things like anonymization of data, so you can't trace back an individual's data back to the identity of the person themselves. That's critically important, and is the starting point for a lot of machine learning. And it's important to note that things like privacy protection and ethical use of data are now, because they're such fundamental constraints. You're absolutely right. 5 years ago, this wasn't a big topic at the big machine learning conferences. Now there are whole streams on differential privacy, ethical use of data, and bias. And so there should be, because what that means is AI has come of age, it's impacting society, and society has realized, look, it's not the Wild West. There's, society has rules of engagement, and AI has to fit into those. And it changes the technology. So if we want to build a system now, we have to construct a system so that you can't attack it and uncover the training data and thereby reveal patient information, of course. So a system has to be so robust that you've ensured the privacy of all the patients who have very generously consented to have their data used for medical research.
Do you think it will lead to a situation where some subject areas where the data is perhaps less sensitive, like, I don't know, driving, what you see out of your windscreen isn't as sensitive as what you see inside your abdomen. So do you think that will cause a divergence in the speed at which AI techniques get applied in different subjects? I mean, yours in particular will, it seems like you're more
Absolutely.
vulnerable than some would be.
Totally agree. So those settings where data are freely available, and like the public setting that you've described, you see a lot of speech recognition, particularly in speech recognition, which is one of the canonical areas by which the progress of AI is communicated to the public. You see a lot of speech recognition systems really accelerating in leaps and bounds, when those data sets are vast and publicly available. For data sets where they're not so publicly available, technologies might be more limited and performance suffers as a result. And it comes back to what I was saying. The regulation and data availability does constrain scientific progress because it constrains the availability of data. But that's something that a modern builder of AI systems must take into account if the system is in any way useful in society. You have to think about the ramifications of the research that you're doing. In the good old days, because I'm such an old man, I can talk about the good old days. I'm far older than I look. It used to be that we would be chartered engineers, and every chartered engineer would adhere to a code of practice to do with duty to society and only signing off on a project when they know there was no danger to the public and those sorts of things. And that was specific training that every engineer had to go through. You can come to AI from very, very many different directions now, not just the good old-fashioned engineer who's done a chartered engineering course. And so I have seen, because of there's so many different ways into AI, that not everybody is as cognizant of that. But that's something, as I say, in recent years, the AI community has really taken this on board. And come to an AI conference, as I'm sure you do, you will see, as I've said, workshops on ethics, bias, differential privacy, etc., where the emphasis is on protecting the data and constructing useful systems, even though progress is slower than the hypothetical case where all data are freely available and data grow on trees.
I'm wondering, because we've gone through over the last few decades a number of AI winters. And the previous AI winters, as far as I can tell, were really caused by scaling issues. That techniques that showed promise then didn't scale up to solve real-world problems, and people got disillusioned and the money drained away from the thing for a few years or a few decades. I'm wondering whether the data sensitivity might be a reason for a new AI winter, or actually whether you feel there are other roadblocks and dangers on the road to further development.
Good question. Bear in mind the first AI winter, by which I think most people would recognize that as being synonymous probably with the dot-com bubble bursting. There was a lot of progress in early machine learning in the 90s on neural networks. I remember the first second Terminator film, Arnold Schwarzenegger saying, "I have a neural network processor." That was the big scientific drop into my childhood cultural references as far as AI goes. But that so-called AI winter was caused because there was so much overpromise. The whole world's going to be revolutionized in the late 90s by AI. Your cybernetic organism for the future has got one as his CPU, etc., etc. And obviously there was a failure to deliver, and the hype proved to be hype. But surely it was ever thus. Right? So people get very excited about new developments, and the money follows. Venture capitalists and so forth want to back the next big thing. I noticed that, as I'm sure you've seen, funding for startup companies and new companies. The bubble has burst, I think, on AI to some degree, in the sense that a couple of years ago everything had to be AI. I would even listen to companies that make prosthetic knees. They had the AI prosthetic knee. Not to demean anyone who's making prosthetic knees, but personally I can quite see the marriage of the two disciplines, which represents the fact that you had to be seen to be talking about AI, and funding would follow, and that bubble has burst. It was maybe a small winter, in the sense that what has remained is real AI, which is actually having impacts on all the different sectors that we know as being important to us. So, finance, healthcare, social media, you know the list as well as do I. AI is now part of our daily life, and it's really hard to do without those things. And I think that's the difference. Now the translations have been made, the successes have been demonstrated, and in my field, in healthcare, the evidence, I won't say it's an ongoing effort, but the evidence is beginning to be shown that well-constructed, thoughtful AI-based projects have a role to play in a clinical pathway. It's not necessarily true that humans don't need a bit of help in some areas, even if it's just automating routine tasks. So it's here to stay. It has improved so much of our lives, and as because of that point, we're seeing a massive growth in the number of people who want to do AI as well.
But I can see that there are many, many areas where applying what we already know could generate tremendous benefit, and that's a sort of low risk because we already know it works, we already know how it works and how to make it work, so it's a case of picking the low-hanging fruit. But I'm wondering whether you sense or worry at all about a limitation, that we're sort of going to hit an asymptotic curve in terms of the capability. In other words, can we just make these models bigger and bigger and they get better and better?
Yeah.
Or do you? I obviously nobody knows the answer to this. I was just interested in your gut feel.
You're absolutely right. So where progress is being made at the moment, it's in the sort of low risk areas where we know it's going to work, and that's why it's being permitted to be trialed and used and so on. There are obvious limitations to machine learning, like things like causality. So that when we construct a machine learning model, we have to think about the way it's trained. You show it lots of examples and you teach it what you would like it to do with those examples. And it's associating the inputs to the outputs. It's not learning causal rules. It's not saying that one thing causes another, nor is it outputting any deeper understanding other than that association that it's learned. So the field of causality in AI is a very hot one. It's also a really difficult thing to do, because obviously to construct AI systems which can think about causality, although immensely valuable, there's a problem of counterfactuals. You don't know what's not going to happen. You've got lots of examples of what happened, but you might not have examples of what didn't happen because it didn't happen. So how you handle that level of uncertainty is tough. And those projects are, that branch of AI is fascinating. And I think without that, AI would be much poorer, because we must understand that we are just associating inputs and outputs, or we're even in machine translation. We're showing it a corpus of literature from the EU's very many languages, and those are documents which are associated, and so it's learning those associations. We've talked about the GPT-3 model, which is a huge one that does that for sequence-to-sequence translation, we call it, but it's not learning anything deeper than an association.
I'm fascinated you bring up the causality aspect, because I sense that's one of the less fashionable and somewhat controversial areas, certainly much less mainstream than the classic deep learning stuff. And I'm wondering whether you can sort of identify, to close, some of the unfashionable or perhaps less well-known areas of AI that people sort of looking to get into the subject, or perhaps wanting to broaden their knowledge. Are there any pointers you could give of, away from that mainstream deep learning area that you think show promise?
So much of mainstream deep learning, as you call it, has been commoditized to the point where, as I say, you can either get someone who's not very experienced to get quite a long way, which is great. I mean, democratizing ML is a good thing, and having school kids who are able to construct models is brilliant. But to answer your question explicitly, apart from causality, which itself is a really maths-heavy discipline, which is I think a good thing. That's why people like me exist. There's also meta learning is a huge field. So how AIs can help a human construct an AI. So we're we're used to AI augmenting routine tasks, how we scale to truly vast quantities of data with models that are immensely complex and that humans can't necessarily optimize themselves, whereas once they might have hoped to do so. Having an AI to help guide that process and to help construct the models is also a super hot topic, of course, as models get bigger and as data sets get more massive. I would say, in my particular discipline, or a pet interest of mine, I mean, the driving force of a lot of the research that I do, is that we really care about making AI systems that work, that get out into the real world. And in my case, that's healthcare. So that degree of reliability engineering, that degree of avoiding the catastrophic failure, that's the system that's sufficiently robust for it to be used in anger in a safety critical way. I think that's also, it's clearly super exciting for a lot of industries, but is a little bit disjoint to what you might learn on a basic machine learning course.
Well, David, thank you very much for your time, and I hope you've inspired some people, and the very best wishes with all your future research.